This video is on rigid body rotations. Rigid means it's an object that you cannot compress or stretch or twist or change its shape. So it's an object that's rotating. Question 1. State the equation, define each variable, and give the units for torque. So torque is this equation, R cross F, or RF sine theta, where theta is the angle between R and F. So it has units of meters, R, and newtons, F, and sine theta has no units. This does not have the units of joules, even though it has the same units as joules, because this has nothing to do with energy or work or transfer of energy. So your fingers from your right hand are in the direction of R and they bend towards F. Your thumb is in the direction of torque. So for linear motion or translational motion, we need a force to make an object speed up, slow down, or change direction. For circular motion, we need a force to make an object speed faster or speed slower. But it's always about rotating. So torque is not about moving an object linearly. It's about making objects rotate. So if you want to rotate an object, you want to make sure F is as big as possible and R is as far away from the center of rotation as possible, and theta is 90 degrees, because sine of 90 is 1. So look at this image here. Look at R1, that's radius 1 times F1. That's going to give you a big torque. Look at radius 2 times F2. You know, the angle between R2 and F2 is 90 degrees, which is good. But you see R2 is not as long as R1. So the torque is not as great as R1. Look at R3, F3. So R3 is smaller, F3 is shorter. Sorry, R3 is shorter, F3 is smaller. And you notice that it's going to rotate in the opposite direction, R3 and F3. And R4 and F4, if you multiply the two, the torque from R4, F4 is going to rotate in the opposite direction as R1, F1 and R2, F2. So R1, F1 plus R2, F2 makes the object rotate clockwise. R3, F3 plus R4, F4 makes the object rotate counterclockwise. And the sum of these four torques will tell us whether the object rotates clockwise or counterclockwise. So this whole RF sine theta, it should remind you of work is equal to FD cosine theta, where theta is the angle between F and D. Question 2, state the equations for Newton's second law of motion for linear or translational motion, and Newton's second law of motion for angular or rotational motion. So what we learned earlier is for linear or translational motion, sigma F equals ma. For circular motion or angular motion, we have sigma torque equals I alpha. So torque takes the position of force, and I takes the position of mass, and alpha takes the position of acceleration. So what I highlighted here is for linear motion or translational motion. What I highlight here is for circular motion or angular motion. Question 3, define and state the conditions for translational equilibrium and rotational equilibrium. Remember, for translational equilibrium, sigma F is 0, A is 0, V is constant. For rotational equilibrium, sigma torque is 0, alpha is 0, and omega is constant. Question 4, state the equations for power for linear motion and for rotational motion. So for linear motion, we had power is equal to work over time, or change in energy over time. Now we have torque times omega, because this was equal to FV. And this is instantaneous. That means at a very specific time, we're going to multiply F times V. And that's the same thing here for rotational motion. Question 5, state the equations for linear momentum and angular momentum. Also state the equations for linear impulse and angular impulse. So for linear or translational momentum, P equals mv. For rotational, L is equal to I omega. So M now becomes I for rotational motion, and V now becomes omega. So remember, J is impulse equals delta P. Now we're going to have L equals angular momentum, which is equal to delta I omega. Question 6, state the equations for translational kinetic energy and rotational kinetic energy. We're going to go from 1/2 mv squared to 1/2 I omega squared. So m becomes I, v becomes omega. And remember, L equals I omega. So if you want to rewrite this, you could rewrite it as this. L squared over 2I. Question 7, state the law of conservation of linear momentum and the law of conservation of angular momentum. Also state their equations. So the law of conservation of linear momentum says if there are no external forces, then the total linear momentum in a closed system is conserved. P initial equals P final, where P equals mv. This law is best understood by understanding a few examples, and we've already seen these examples in the previous video. Now this is the law of conservation of angular momentum. If there are no external forces, then the total angular momentum in a closed system is conserved. So L initial equals L final, where L is equal to I omega. So we'll see an example or two later, hopefully, but think about an ice skater. When he or she is spinning and he or she has her hands far apart, the ice skater is moving slowly. When he or she moves, the ice skater moves the hands closer together, they spin faster. Now this is because the moment of inertia decreases when you move your hands inside. So if I gets smaller, omega gets bigger. Why? Because L is constant. It's conserved. And if you move your hands outside, I gets bigger, so omega gets smaller, because L is constant. Question 8. A uniform disk which has a mass of 3.5 kilograms and a radius of 28 centimeters is accelerated from rest by a tangential force of 28 newtons applied to the outer edge of the disk. Part A. What is the moment of inertia of this disk? You need to know that the moment of inertia of a disk is 1/2 mr squared. Part B. What is the magnitude of the torque being applied to this disk? It says torque, that's RF sine theta. Theta is 90 degrees because it's a tangential force. Part C, what will be the angular acceleration of this disk? Remember, torque is equal to I alpha, so let's just solve for alpha. Part D, what will be the angular velocity of this disk after 8 seconds? So this is a Suvat equation from linear motion that becomes an equation for angular motion. Part E, what will be the linear velocity of a point on the outer edge of the disk at the end of 8 seconds? V equals R omega. Part F, what will be the angular displacement of this disk during the 8-second period? So we're going to use this equation here. Change in displacement equals V initial plus V final over 2 times time. And we're going to convert it to change in angular displacement equals angular speed initial plus angular speed final divided by 2 times time. Part G, what will be the linear displacement of a point on the outer edge of this disk during the 8-second period? Linear displacement, S equals R theta, solve for S. It's already solved for. Part H, how much work was done on this disk during the 8-second time period? It says work. It's equal to FD. But we have to translate that to what? Torque theta. F becomes torque, D becomes theta. Part I, what will be the final angular momentum of this disk? P equals mv, so now it's L equals I omega. Part J, what is the final angular kinetic energy of this disk? 1/2 mv squared becomes 1/2 I omega squared. Question 9, a bicycle wheel is mounted as in the lab and as shown below. This wheel has a mass of a wheel is 6.55 kilograms. A radius R sub W is 38 centimeters and is in the shape of a ring. A mass M equals 1.85 kilograms is attached to the end of a string which is wrapped around an inner hub which has a radius R sub I is 5.4 centimeters. Initially, the mass M is a distance 72 centimeters above the floor. Assume friction is negligible. Part A, what will be the resulting angular acceleration of this wheel? So sigma F equals ma becomes sigma torque equals I alpha. And they want us to solve for angular acceleration. So we know I this is mg here. Sorry. This is RF. Okay. 0.0540 is R. And F is the force of gravity, which is 1.85 kilograms times 9.81. So, sorry, this is the mass of the box. This is this mass here on the bottom. So RF is equal to I alpha. And 6.55 kilograms times 0.380 meters squared is I. And we're just going to solve for alpha. Part B, how long will it take for the mass M to reach the floor? So we have this Suvat equation, and we're going to convert it to this angular motion equation. S equals R theta. We know S, we could solve for theta. So we know theta final is going to be this. We end up getting 5.07 seconds. Part C, what would be the total angular displacement of the wheel during the time in which the mass M is falling to the floor? So S equals R theta. This is the radius for the wheel. We already solved this from part B. Sorry. We were given the distance above the floor, 72 centimeters. And we get 13.3 radians. Part D, how much work was done on the wheel by the external torque as the mass M falls to the floor? So this is the Suvat equation. We convert it to an angular motion equation. And we have 1/2 I omega final. Because omega initial is 0. So we need this omega, so alpha t to be here. Part E, what would be the angular kinetic energy of this wheel just as the mass m reaches the floor? So kinetic energy is 1/2 I omega squared. We have this Suvat equation, which becomes this when it comes to angular motion. Omega initial is 0, theta initial is 0. So solving for omega final squared, we get 2 alpha theta final. Take the square root to get this to be omega. Kinetic energy is 1/2 I omega squared. To get our results. Question 10. A sphere which has a mass of 2.1 kilograms and a radius of 35 centimeters is rolling along a horizontal surface with a velocity of 12.2 meters per second when the sphere encounters an inclined plane which meets the horizontal at an angle of 22 degrees. So something like this image. Part A, what is the angular velocity of the sphere? V equals R omega, solve for omega. Part B, what is the linear kinetic energy of the sphere? We're going to use 1/2 mv squared. Part C, what is the angular kinetic energy of the sphere? 1/2 I omega squared. Part D, what is the total kinetic energy of the sphere? We're going to do parts B and part C, which is a translational kinetic energy, also known as linear, plus rotational kinetic energy, also known as angular kinetic energy. Part E, how far up this incline will the sphere roll before it comes to a halt? So total energy initial equals total energy final. This is law of conservation of energy. So we have the total kinetic energy on the left, translational and rotational, equals mgh on the right. Solve for h. Now h is the height. It's asking for how far up the incline. So this is asking us for the hypotenuse. So this gives us the hypotenuse. Part F, how long will it take for the sphere to come to a halt? So here we solved for angular displacement. Here we're going to use a Suvat equation and convert it to an angular motion equation to solve for alpha. Finally, we're going to use this Suvat equation and convert it to an angular motion equation to solve for time. Part G, what will be the linear acceleration of the sphere as it rolls up the incline? So linear acceleration. We have this Suvat equation and we convert it to an angular motion equation and we solve for alpha. A equals R alpha. So we could obtain A. Part H, what will be the angular acceleration of the sphere as it rolls up the incline? So it was already solved for here. Part I, what is the moment of inertia of the sphere? I is equal to 2/5 mr squared. Part J, what will be the net torque acting on the sphere as it rolls up the incline? Torque equals I alpha. Part K, what will be the gravitational potential energy of the sphere as it comes to a halt on the incline? mgh. Question 11, a disk which has a mass of 12 kilograms and a radius of 65 centimeters sits at the top of an inclined plane, which is 8.4 meters long and 1.5 meters high. At t equals 0, the disk is released and is allowed to roll to the bottom of the incline without slipping. Part A, what is the gravitational potential energy of this disk as it sits at the top of this incline? So just use mgh. Part B, what will be the total kinetic energy of this disk as it reaches the bottom of the incline? E initial equals E final. So this is the same answer as in part A. Part C, what will be the linear velocity of this disk when it reaches the bottom of the inclined plane? So kinetic energy final is equal to 1/2 I omega squared. For a disk, I is 1/2 mr squared. And we know V equals R omega. Part D, what would the linear velocity be if the disk is replaced by a sphere? So now we're going to change the moment of inertia to 2/5 mr squared. Part E, what would the velocity be if the object was a ring? So now we're going to replace 2/5 mr squared to mr squared. So when all of the mass is on the outside, the final velocity is 5.42. When it's a sphere, it's 6.92. And when it's a disk, it's the fastest at 7.67. Question 12. A solid chocolate sphere with a mass of 9 kilograms and a diameter of 80 centimeters is placed on top of a rough incline with a length of 6 meters at an angle of 50 degrees. The solid chocolate sphere begins from rest and rolls down the incline. Now, we need a rough incline because if it was smooth, there would be no rotational motion. It has to be rough, so the object actually rotates. So part A, draw a figure. That's a good figure. Part B, what is the initial height of the solid chocolate sphere? Let's just use trigonometry. Part C, how many revolutions will it take for the solid chocolate sphere to reach the bottom of the incline? So S equals R theta, X equals R theta. We solve for theta. And we want revolutions, not radians. So we multiply by 1. 1 revolution is equal to 2 pi radians. So what's in parentheses is 1. Part D, what will be the final linear speed of the solid chocolate sphere at the bottom of the incline? So use the law of conservation of energy. Potential energy plus kinetic energy in the beginning equals potential energy plus kinetic energy in the end. So we have this equation here. We know I equals 2/5 mr squared and V equals R omega. So plug that in here. V initial equals 0 and H final equals 0. So plug that in also. So using algebra, we end up getting this equation. And we could solve for V final. And we get a value. Okay. This is important. Part E, what would be the final angular speed of the solid chocolate sphere as it sphere at the bottom of the incline? Angular speed, V equals R omega, solve for omega. Part F, what would be the angular acceleration of the solid chocolate sphere? Use this Suvat equation, convert it to an angular motion equation, and solve for alpha. Part G, what would be the linear acceleration of a solid chocolate sphere? A equals R alpha. Part H, how long will it take for the solid chocolate sphere to reach the bottom of the incline? So we have two methods. We could use this angular motion equation, or we could use this angular motion equation. Question 13, a solid chocolate sphere with a mass of 8 kilograms and a diameter of 70 centimeters is rolling to the right on a frictionless horizontal surface with a linear speed of 6 meters per second. The surface then becomes rough with a coefficient of dynamic friction of 0.150. So it's frictionless on the left side, but it was made to rotate in the beginning. So that's why it's rotating. Part A, draw a figure. Part B, what is the angular speed of the solid chocolate sphere as it rolls along the frictionless horizontal surface? V equals R omega. Solve for omega. Part C, what is the angular acceleration of the solid chocolate sphere as it travels along the rough surface? So sigma F equals ma becomes sigma torque equals I alpha. And what force is on this rough surface to make this ball slow down? It's minus force of friction. And we plug in I, which is 2/5 mr squared for a sphere. Force of friction is mu Fn. Force normal is mg. Solve for alpha. Part D, what is the linear acceleration of the solid chocolate sphere as it travels along the rough surface? So just use A equals R alpha. Part E, how many revolutions of the solid chocolate sphere complete as it travels along the rough surface? So we're going to take this Suvat equation, and then we're going to convert it to an angular motion equation and solve for theta final. And then we're going to use a unit conversion to convert it from radians to revolutions. Part F, how long does it take for the solid chocolate sphere to stop along the rough horizontal surface? Take the Suvat equation, convert it to an angular motion equation, and solve for time. Or you could have taken this Suvat equation, converted it to an angular motion equation to solve for time. Question 14. A block of mass m1 equals 7 kilograms sits at rest on a horizontal surface with mu equals 0.2. Mass m1 is attached to a massless string which is wrapped around a pulley. Another massless string is wrapped around the same pulley and is holding another block of mass m2 equals 47 kilograms in the air. The pulley is a cylinder which has a mass of m sub cylinder equals 12 kilograms and diameter of 10 centimeters. Part A, draw a free body diagram. Remember, circle the objects, label the forces, put an x and y axis. And finally use the equation F equals ma. Now this problem looks familiar when we were learning about Newton's second law of motion. The only difference now is we're going to mention the rotation of this pulley. The pulley is not frictionless, the pulley is not massless. The pulley has a mass. And it has a dimension, a diameter of 10 centimeters. Part B, what is the common linear acceleration of the system? Part C, what is the force of tension on the two massless strings? So, look at mass 1 first. Sigma F sub y equals m1 a sub y1. We know the object is not jumping up and down. So force normal 1 equals force gravity 1 equals mg. So this is the vertical y-axis only for mass 1. Sigma f sub x1 equals m1 a sub x1. What forces are on the horizontal axis or the positive x-axis for mass 1? It's plus force of tension minus force of friction. Plus force of tension minus force of friction. What is force of friction? It's mu Fn. So now we have one equation in yellow. Let's take a look at mass m2. Remember, positive x is clockwise. So what forces do we have on mass 2? Plus force of gravity minus force of tension 2. So plus mg minus force of tension 2. Now finally look at this pulley. It's going to move clockwise, yeah? Sigma torque equals I alpha. So R ft2 minus R ft1 equals I. This is the moment of inertia of the cylinder times alpha. Remember A equals R alpha. So substitute that in here. So the radius of this cylinder times force tension 2, that's Rf, that's torque, minus the radius of the cylinder times force tension 1. That's equal to I alpha. So we could simplify to get this equation in blue. So from symmetry, A sub x1 equals A sub x2 equals A sub xc equals A. So now we have these three equations, bam. Let's plug in the numbers that we know, bam. 3 equations, 3 unknowns is painful to solve. We're solving for force tension 1, force tension 2, and acceleration. So we simplify it to be this, and I move everything, all the unknown, all the variables on the left side, and the number on the right side. So if we have 3 equations and 3 unknowns, I could go to matrixcalc.org and solve. This is ft1, this is ft2, this is A. And we could find the angular acceleration of the cylinder by using the equation A equals R alpha. So solve for alpha. Question 15, a thin disk with a mass of 250 grams and diameter of 40 centimeters is spinning with an angular speed of 3 radians per second. A point mass with a mass of 350 grams strikes and sticks to the top of the thin disk from the edge. What is the final angular speed of the system? Do you remember the examples of law of conservation of linear momentum? If you don't, go back to that video and look at those examples. It's like you have 2 objects hitting each other and sticking together and moving together. So we're going to have angular momentum initial equals angular momentum final. So I initial omega initial equals I final omega final. So this is angular momentum initial. This is angular momentum final. You notice the I on the left-hand side is the same as the I for the right-hand side, except for that point mass here, which is highlighted, that sticks. So because I final is greater than I initial, omega final is going to be less than omega initial. Question 16. A star which has a mass of 4.6 times 10 to the 30 kilograms and a radius of 9.3 times 10 to the 8 meters rotates on its axis once every 16 days. Part A. What is the moment of inertia of the star? So for a sphere, I is equal to 2/5 mr squared. Part B. What is the angular velocity of the star? So we went from 2 pi radians every 16 days, and we want to convert that to radians over seconds. Remember, these three brackets that have been highlighted, each bracket is equal to 1, because the numerator 1 day is equal to the denominator 24 hours. The numerator 1 hour is equal to the denominator 60 minutes. Part C. What will be the linear velocity of a sunspot that is located on the equator of the star? So V equals R omega. Part D. What is the angular momentum of the star? P equals mv is for linear momentum. L equals I, omega is angular momentum. So we know I, we know omega. As this star finally consumes most of its hydrogen and fuel, it starts to contract and heat up until it gets hot enough to start burning helium as a fuel. The burning of the helium fuel is very intense, and the star quickly becomes a red giant as it expands to a new radius. So it gets bigger. What would be the angular momentum of this star after it has expanded to a red giant? Well, angular momentum is conserved, so angular momentum initial equals angular momentum final. Part F, what would be the angular velocity of the star after it has expanded into a red giant? So let's use this equation. L initial equals L final, I initial omega initial equals I final omega final, and let's just solve for omega final. Part G, what will be the new rotational period of the star in days after it has become a red giant? So period has units of time, so you need to make sure time is in the numerator. So the answer is 400 days per rotation. After a few million years, the helium fuel is all used up and the star again begins to contract, becomes extremely hot, and then undergoes a massive supernova explosion. After the explosion, the remaining neutron star has a radius of only 1,200 kilometers. Assume that the mass of the star remains unchanged. Part H, what will be the angular momentum of the star after it has collapsed into a neutron star? Angular momentum is conserved, so L initial equals L final. Part I, what will be the moment of inertia of the star after it has collapsed into a neutron star? Moment of inertia of a sphere is 2/5 mr squared. Part J, what will be the angular velocity of the star after it has collapsed? Once again, angular momentum initial equals angular momentum final. Part K, what will be the rotational period of the star in seconds after it has collapsed? So we just want to convert it to seconds per rotation, because the units of period is time, and they want the period in seconds. Question 17. You are holding a sphere which has a mass of 3.55 kilograms and a radius of 0.380 meters by an axle inserted vertically through the center as shown below. initially the sphere is rotating about its vertical axis 12 times every 5 seconds. So let me show you where it's the figure. It's this. Look at the before image. It's rotating. Part A, what is the moment of inertia of the sphere? It's 2/5 mr squared. Part B, what is the magnitude of the angular velocity of this sphere? You want radians over second. They gave us rotations over second. Part C, what is the magnitude of the angular momentum of the sphere? L equals I omega. Part D, what is the direction of this sphere's angular momentum? So we need to place the fingers from our right hand in the direction of the angular velocity. The direction of your thumb is in the direction of the angular momentum. The thumb in your right hand points up, so the direction of the angular momentum is up. Assume that you are sitting on a freely rotating chair, that your mass is 65.5 kilograms, and that your radius of gyration is 14 centimeters. Suddenly you invert the sphere as shown below. Part E, what will be the sphere's final angular momentum? Well, you just flip it. So it becomes minus 3.09. Originally we had plus 3.09. Part F, what would be the direction of the sphere's final angular momentum? Follow these instructions again. So the direction of the angular momentum is down. Take a look at this image. The after image. Fingers in the direction of the angular speed. Thumb points down from the right hand. Part G, what would be the magnitude of your final angular momentum? L initial equals L final. L equals I omega. Part H, what is the magnitude and direction of the impulse delivered to the sphere? We'll just use this equation here. Part I, how much work was done in inverting the sphere? We'll just use this equation here. Question 18. A ladder has a mass of 20 kilograms and is 6 meters long, is leaning against a frictionless wall. The ladder is at rest and makes an angle of 30 degrees from the wall. Draw a figure and write down the equations for static equilibrium. So we want to make sure this ladder is not moving horizontally. We want to make sure this ladder is not moving vertically. And finally, this third equation, we want to make sure this ladder is not rotating clockwise or counterclockwise. So this yellow equation is all of the horizontal forces. This green equation is all of the vertical forces. Now, let's talk about this third equation here, torque equals I alpha. We don't want this ladder to rotate. So let counterclockwise be positive if the pivot is from the floor. So if we're letting the axis start from the floor to the ladder, what forces do we have? Well, we have R to the middle of the ladder times force of gravity, and we have R, the big R, the whole ladder radius, times the force normal 2. So that's going to be this equation here. So this first part here is the whole length of the ladder, which is R, times F, which is force normal 2. Because remember, torque is RF sine theta. And what's the angle of this orange? It's 120 degrees. The second part is going to be RF. So what is R? It's going to be R over 2. What is F is the force of gravity, because we're treating the whole mass of the ladder to just be at the center. So then we could simplify this equation. Now, or if the pivot is from the wall, meaning we're saying R equals 0, the origin starts at the wall, it's going to be this whole big R, which is the whole length of the ladder, times force normal 1, times this angle in green. That angle in green is 150 degrees. Minus R over 2 force gravity sine theta, which means R over 2 is half the length of the ladder. We're saying all of the mass of the ladder is just at the center of the ladder. That's R over 2. Force of gravity sine of 30 degrees, that's the sine of this gray part here. You see a small gray part. And that's equal to 0 because we want alpha to be 0. And we can just simplify. So we could use any one of these two blue equations. Question 19, write down the common terms and equations for rigid body mechanics. So here we go. 360 degrees is 2 pi radians. These three equations convert Suvat equations to rotational motion equations. Omega is 2 pi f. These are the Suvat equations that have been converted to angular motion equations. F equals ma becomes torque equals I alpha. Sorry, torque. F equals ma. This is wrong. This should be torque equals I alpha. Mass becomes moment of inertia. Kinetic energy translational becomes kinetic energy rotational. 1/2 mv squared becomes 1/2 I omega squared. Here we go. F equals ma becomes torque equals I alpha. That's correct. Work equals Fd cosine theta becomes work equals torque times theta. Power equals Fv becomes power equals torque times omega. And P equals mv equals L equals I omega.